Now we are getting to a partially out estimator. I create some data which I simulate. I'm creating table from scratch. I create Z, which is the confounder, which is a random draw from uniform distribution with minimum 0 and maximum 5. And I draw 1000 observations from this distribution. Then I create treatment variable, which is 5 multiplied by the confounder plus some noise. And I create Y, which is in 10 is an intercept. I add the treatment, so the treatment effect is 2. I also add the impact of the confounder plus some noise. So then I run a linear model Y on D without the confounder, and I will get that the estimate of D, the impact of D on Y is estimated to be 3.2. But as you can see, it's incorrect because the true treatment effect is 2. So here you have the omitted variable bias. We are omitting Z, which creates this bias for the estimate of D. Now, if we include Z in our regression, voila, the estimate of the coefficient in front of D is 2, which is correct. Now, here you're asked to partial out and get the residuals. So first line is you partial out the confounder from the treatment and you collect the residuals. Now to do the same for Y is just copy this code. Here we partial out Z from Y and we collect the residuals. And final step, we regress Y, no D, on D, no Z. So we regress LM, Y no Z, and D no Z. So we regress the residuals on the residuals. Now let's look at the code for the double selection or partially out your post-lasso procedure. So post-lasso procedure requires us to find the residuals of a post-lasso of Y on Z and residuals of D of a post-lasso of D on Z. So very importantly, we need to make a function that basically gets the residuals. So that makes the step 1 or step 2. This function will take a dependent variable, vector, and the data, which is basically vector of Z. So it takes 2 objects, and then we need to finish the code for this function. I will just copy the hint, but we will go through it. So this is the same code that we had before, where we do cross-validated lasso. We collect the best lambda. We do lasso regression at best lambda, and then we collect the lasso coefficients. Now look here, what is important is that we regress a dependent variable that we supplied on X. And we remember to put dependent variable here so that the nickname that we gave to the object that we are passing from the outside environment. Here, this step is also that we already saw before. We collect all the coefficients and we filter out those that were set to 0 by lasso. Then we run the OS. We take our data that is passed by the function and we mutate dependent variable. So dependent variable is a vector and we assign a new column within the data set that we passed called data, and we create a new column which is our dependent variable. Then we say select dependent variable, and then we want to select lasso coefficients and coef names. Linear model dependent variable. No. Linear model is, we should take, yes, dependent variable. Now you see, this one will take the column called dependent variable from the data that we supply. And we regress it on all of the variables that we selected. And then residuals. Okay, the next step is to apply this function get residuals on the dependent variable. equals to the data set column 1, and the data would be the data set itself, but we should deselect from that data set y and z, because we want only the potential confounders to be passed as the data here. Now d on z is the same, dependent variable is now d, and data is the same. And step 3 is we regress residual y on residual d. Let's run the code. And voila. So this is actually means 0.98. So it's actually quite close to the true treatment effect. So partialing out worked very well here. Now let's see how it will work when we simulate it 100 times on 100 different samples that we created.